Section 1.4, the matrix equation AX equal B. Linear combinations can be viewed as a matrix vector multiplication. In this definition, if A is an m by n matrix with columns that are vectors a1, a2 through an, and if X, the vector, is in Rn space, meaning it has n entries, then the product of our matrix A and our vector X, denoted by AX, is the linear combination of the columns of A using the corresponding entries in our vector X as weights. So we see this kind of laid out for us here. We have AX, and so each column of A is a vector, and we're going to multiply that by the entries in X, and they're going to be weights here in our linear combination. And now we can see it laid out. Right here is my matrix A, and it's a 3 by 2 matrix. And then here is my vector X, and we see that its size would be a 2 by 1. So it would be in R2 space since it has 2 entries. So our linear combination would then be to take each entry of X and multiply it by the corresponding column. So this is the first column of A multiplied by the first entry in our vector X. So we have 7 times the first column of A, which we'll call A1. And then we'd have negative 6 times the second column of A. And we would simply distribute that and multiply, in this first case, 7 by each entry and get this vector here. Same thing with negative 6. And then we would add the individual entries up. So then we would have that when we multiply A times X, we get a vector that is a 3 by 1. So a little something to take note of: if I'm multiplying, in this case, A times X, I look at the dimensions. A was a 3 by 2, and then X was a 2 by 1. When I'm multiplying, as long as the inner dimensions match, and we have a 2 inside here, then my resulting equation will be the outer dimensions. My resulting answer. So I have a 3 by 1 vector as my answer, and that's what we saw happening. In this example, we want to write down the system of equations corresponding to the augmented matrix below, and then express the system of equations in vector form, and finally then in the form AX equal B, where B is a 2 by 1 vector. So first, as a system of equations, we have 2x1 plus 3x2 plus 4x3 equals 9, and then negative 3x1 plus 1x2, or just x2, plus 0x3 equals negative 2. Now, as a vector equation, I'm going to essentially take my system of equations and pull out x1. So if I pull out x1, then I'm left with a single vector, which is 2, negative 3. And then I'll do the same thing with x2, and I'm left with the vector 3, 1. And then lastly, we'll pull out x3, and we have the vector 4, 0. And then it would be equal to my answer vector, which was 9, negative 2. And now, as a matrix equation, I'm going to look back at my vector equation, and I'm going to say that these vectors were the columns of my matrix. So we're going to call these A1, A2, and A3. And so we'll take our matrix, and it'll consist of those as our columns. So I've got 2, negative 3, 3, 1, and 4, 0. And so that's going to be my matrix A. And then I'm multiplying that by X, and X has x1, x2, and x3 in it. And so then this would be my vector X. and then it equals my answer vector, which was 9, -2, and that was b. And we do see that this is a 2 by 1 vector. So we just saw 3 equivalent ways of viewing a linear system. Number 1 as a system of linear equations, 2 as a vector equation, given here, or 3 as a matrix equation, Ax equal b. So that leads us to theorem 3. If A is a m by n matrix with columns a1 through an, and if B as vector is in Rm space, then the matrix equation Ax equal b has the same solution set as the vector equation x1a1 plus x2a2 plus all the way up to xn times an equals b, which in turn has the same solution set as the system of linear equations whose augmented matrix is made up of the vectors a1 through an and the vector b. So the definition of Ax leads to the following fact. The equation Ax equal b has a solution if and only if our vector b is a linear combination of the columns of A. In this example, we're given a matrix A and a vector b. Is the equation Ax equal b consistent for all b? So first we want to look at the augmented matrix corresponding to Ax equal b. And this is made up of the columns of our matrix A, and then b serves as the last column for our augmented matrix. So we want to row reduce this. I'll multiply my first row by 3 and add it to my second row, and then I'll multiply by a -2 and add it to my third row. And when you do this, you should come up with this matrix. So we can answer our question by looking at our last row here, and we see that we have 0 equal to -2b1 plus b3. So we want to know if it's consistent, and the only way that it's consistent for all b is if there are no choices for b1 or b3 that would make this non-zero. And that's not true. I could choose a number for b1 or b3 and this equation would come out to be a non-zero number, which would make this equation false. So Ax equal b is not consistent for all b, since some choices of b will make -2b1 plus b3 non-zero. However, it is consistent if my equation -2b1 plus b3 equals 0. So we can state it this way. x1a1 plus x2a2 plus x3a3 is equal to b if and only if my expression -2b1 plus b3 is equal to 0. In this definition, we say that the columns of A, A1 through AP, span Rm, M space, if every vector B in Rm is a linear combination of my vectors A1 through AP. And so we can write it that the span of my columns of A is equal to Rm. And that leads us to theorem 4. This is an extremely important theorem, so we'll kind of star it here. You want to make sure that you remember theorem 4. It'll come up a lot as we do proofs from now on. So we're going to let the matrix A be n by n, and the following statements are logically equivalent. A, for each vector B in Rm space, meaning it has m entries, the equation Ax equal b has a solution for each b, so for every b. Each B, or every B in Rm, is a linear combination of the columns of A. C, the columns of A span Rm. And D, A has a pivot position in every row. So what we're seeing is that if one of these statements is true, then they're all true. And if one of these statements is false, then they're all false. So it's a pretty important theorem. So we're going to look at a proof, and this is just an outline of the proof. We're going to look at statements A, B, and C. They are logically equivalent. So to complete the proof, we need to show that A is true when D is true, and A is false when D is false. So first we're going to suppose that D is true. Then we can row reduce our augmented matrix with A, B. So given a vector B in Rm, we can row reduce our augmented matrix AB to some new matrix UD for some vector D in Rm. And that's what this is saying here, that we are using some row reduction to reduce our matrix AB to a new matrix UD. And each row of U has a pivot position, since we assumed to begin with that D was true, meaning that A had a pivot in every row. Then just by doing row operations, we didn't change the fact that going from our matrix A to this new matrix U, we still have a pivot in every row. So that means there is no pivot in the last column of my matrix UD, meaning that I don't have a row of all zeros and then a non-zero number happening. So I don't have 0 equal a number happening. So since that is true, there's no pivot in the last column, then A is true. I'll have a solution for my matrix equation AX equal B. Now we're going to suppose that D is false, meaning that I don't have a pivot in every row. Then the last row of my matrix U contains all zeros, and we'll suppose that D is a vector with a 1 as the last entry. So what we end up with then is a row of zeros with a 1. So I've got 0 equal 1, which is false. So then my matrix UD represents an inconsistent system. And since row operations are reversible, I can go backwards from my matrix UD to my matrix AB, and thus show that AB is also inconsistent, just like UD was. So that then shows that A is false, meaning I will not have a solution to X equal B for each B. And this is a proof of Theorem 4. In this example, we have a matrix A, which is a 3 by 2, and a vector B, which is a 3 by 1. Is the equation AX equal B consistent for all possible B? We see that A has only 2 columns, and therefore has at most 2 pivots. But A has 3 rows. If there's only 2 pivots, then there can't be a pivot in every row. Since A does not have a pivot in every row, then my matrix equation AX equal B is not consistent for all possible B by Theorem 4. Looking at this example, we want to answer the question, do the columns of A, which is a 3 by 3 matrix, span R3? So we'll begin to row reduce, and we'll multiply the first row by -2 and add it to the second row. And we get this matrix. So what we see then is that we don't have a pivot here. There is no pivot in row 2. So then, by Theorem 4 again, we know that the columns of A do not span R3. So using Theorem 4, if one of them is true, then they're all true. If one of them is false, then they're all false. Now I want you to try, given the following matrix, matrix B, and it's a 4x4, I want you to answer these two questions. Can every vector in R4 be written as a linear combination of the columns of the matrix B? And then do the columns of B span R3? So think about it and try to come up with an answer for each of those questions, and we'll talk about it in class. In this example, we want to compute AX, where A is this 3x3 matrix and X is the 3x1 vector. So from my definition, when I take my matrix A and I multiply it by my vector X, I'm going to take each entry in X and multiply it by the corresponding column of my matrix A. So X1 will be multiplied by the first column of A, X2 by the second, and X3 by the third. And here we'll see it here. And now I want to take X1 and multiply it by each entry in my vector, and the same with X2 and X3. So I'll get the following. So we see that basically we've taken our vectors and put X1 in the first one, X2 in the second, and X3 in the third. And so now I'm going to add each of the entries across, and we get the following vector, which is a 3x1. So the first entry here in the product AX is the sum of products, sometimes called a dot product, using the first row of A and the entries in X. And you'll see that for the second entry and the third entry. So we have a row vector rule for computing AX. If the product AX is defined, then the ith entry in AX is the sum of the products of corresponding entries from row I of A and from the vector X. So we'll first look to see if it's defined, and you remember what I talked about earlier. We'll look at the dimensions. My matrix here is a 2x3, and my vector here is a 3x1. So since the inner dimensions match, we know that we're allowed to do it, and that our answer then is going to be a 2x1. And what we're going to do is we're going to basically do a dot product, and we're going to go across and down as we multiply entry by entry. So we're going to have 1 times 4 plus, then we move to the next entry in that first row, 2 times the next entry in my vector, which was 3, and then plus my last entry in that row, which is -1, times my last entry in my vector, which was 7. And then we'll do the same thing. We're going to go across my second row and down my vector. So I'm going to have 0 times 4 plus -5 times 3 plus 3 times 7. And then we just need to do this arithmetic. So I have 4 plus 6 plus a -7, and we'll get 3. And then I have 0 plus a -15 plus 21, and so we'll get 6. And now, for example B, I want you guys to do this one on your own, and we'll talk about it in class. Theorem 5, if A is an m by n matrix, and U and V are vectors in Rn space, meaning they have n entries, and then C is a scalar, then the following properties are true. If I have my matrix A times the sum of U and V, that is equivalent to my matrix A times U plus my matrix A times V. And then the same thing with my scalar. If I multiply my matrix A by my scalar C multiplied by vector U, that is the same thing as C times A, then times my vector U. And you'll get a chance to examine this theorem in your homework.